Okay, IBAASL2 kids. I did do a little pre-5.4 video that you should go and watch first, but today we're going to get into like the real meat of 5.4. We're going to be using derivatives to interpret certain things about graphs. So the first thing I want to talk about is just graphs in general. So without graphing things on calculators, we can use derivatives to tell us certain things about the graph. For instance, if you plug in an x value into a derivative in this zone of the graph, you will get, or into the original function, you will get negative numbers. That's because there are negative tangents going downhill. But then at this point right here, you will get a horizontal tangent, which has a slope of 0. We're going to start to call these turnaround points because at that point right there, it switches from negative slopes to positive slopes. So here, all these tangents are going to be going uphill, and then here up at the top, we'll get another horizontal tangent, which will be equal 0. That's another turnaround point, and then you'll be going back downhill again. So negative slopes of tangents on this side. Those spots, those horizontal tangent spots, are called turnaround spots, or I think the book calls them turning points, because they turn from either negative to positive slopes or positive to negative slopes. First problem, find the intervals where each function is increasing or decreasing. We're going to do this all without a graphing calculator. So first thing is we're going to take the derivative. So there's the derivative. Now we need to set the derivative equal to 0 because that's going to tell us where the horizontal tangents are. Remember, horizontal tangents are where it switches from positive to negative slopes or negative to positive slopes of tangents. Anytime I'm saying slopes, I mean slopes of tangents. So let's set it equal to 0. Did I take the derivative right? Did I write it down right? That's the question. Hold on. Let me check. I did. Okay, so we need to solve this. If you add 3 to both sides and then divide by 3, we get 1 is equal to x squared. Now we need to square root both sides, but remember, anytime you introduce a square root, you have to do a plus minus on it. So if I do plus minus the square root of 1, that means that x is equal to negative 1 and positive 1 on the turnaround points, the horizontal tangents. So the question is, like, we know that the graph switches from either positive to negative or negative to positive at negative 1, and then it does the same, or not the same thing, but it also switches either from positive to negative or negative to positive at positive 1. Now, without actually graphing it, we need to be able to figure out what's happening. So here's what I do. I put out a line, a number line, and I say we're going to test slopes. I know that something happens at negative 1 and something happens at positive 1. So to be able to tell what's happening around those points, like I want to know what's happening in this zone and this zone and this zone, but I want to know what's happening with the slopes. So what you do is pick a number and check the spot. And we're going to check it in the derivative. Remember, the derivative is 3x squared minus 3. So I'm going to pick a number that's to the left of negative 1. Let's say negative 2. Keep it simple. It could be any number to the left of negative 1, but I'll just pick negative 2, and then I'll plug it into the derivative formula. So then negative 2 squared is 4, and then times 3 is 12, and then you subtract 3 and you get 9. Now, I really don't even care that it was 9. I just care that it was positive. It was a positive number, which means in that zone I just tested, so I just started testing this zone right here, that the graph is going uphill. Remember, positive means uphill. So I will put an arrow right here to remind me that the graph was going uphill in that zone. Now, This spot right here, -1, is usually where it flips from either uphill to downhill or downhill to uphill. But I will check a number just in case. So here, I'm going to plug in like I'm going to pick like a 0. So f prime of 0. Plugging it into the derivative. Remember that the derivative, the slope machine, is right here. So you get 3 times 0 squared minus 3. So that's 0 minus 3, which is negative. Once again, I don't care that it's -3. I just care that it's negative. So that means downhill. Then you pick a number for the last one. I would pick probably +2, but it could be anything. So we'll test f prime of 2, and this equals a positive number. Yeah, if you do 2 squared is 4 times 3 is 12. Oh, you get 9 again. So, oh, wrong color, Jolly, come on. They're going uphill in this direction. So, what that means is that the whole entire curve is increasing on this interval, decreasing on this interval, and increasing on this interval. The way we can say that is that it's increasing. We're going to use IB notation from -infinity all the way up to -1, but not including -1. Then, so that was this section right here. It increases again after +1. So I'm going to unionize that with +1 all the way up to infinity. Now, you don't necessarily have to use the IB notation with the brackets. You could use the alligators. That's fine as well. But that's where it's increasing. Decreasing would be this zone right here, in between -1 and +1. So that would be not including -1. Because it's like, it's not increasing or decreasing at those turnaround points. It's like the tops of mountains and bottoms of valleys. So from -1 to +1, it's decreasing. So then, not gonna make a box? Whatever. The next one, we're gonna do the same thing to figure out where this function is increasing or decreasing and where the turnaround points are. So first thing I'll do is take the derivative. It's just 2x with the power rule. Then we're going to set it equal to 0 to figure out where the turnaround points are. Divide by 2. So the turnaround spot, there's one turnaround spot, and it's at 0. We want to figure out if it's turning from negative to positive or positive to negative. So we will test slopes. Remember that we're testing them in this derivative, y prime equals 2x. That's the slope machine. The only change is at 0, which means we need to test something to the left and something to the right. If you plug in a -1, so we do y prime 2 times -1, you get negative. So that means it's going downhill on this side. And then if you plug in something to the right of 0, like a +1, that of course is a positive number, which means on the side where +1 lives, to the right of 0, it is going uphill. So all I did was pick a number from this zone, test it in the derivative. I got a negative, which means that's going downhill. Then I picked a number to the right of 0 in this zone. I picked +1, put it in the derivative, got a positive, which means it's going uphill. Now, this makes sense because what is this guy? That is a parabola. So if you picture a parabola, x squared minus 1, that means it's a regular parent parabola that's been shifted down 1. So notice that this is certainly a turnaround spot, and on this side it's going downhill, this side is going uphill. So the derivative worked. Just in general, if you're going uphill and then you switch to downhill, this spot is called a local maximum. Now, it might not be the, and it's going to be an XY coordinate. It might not be a global maximum. Global maximum is like, the tallest that the graph gets in terms of Y on the whole thing. But if there's a little spot where there's a little mountain, that's called a local maximum. Local maximum is where it switches from positive slope to negative. See that? It was going uphill, then downhill. So that's a maximum. The flip of that, if you're going downhill, negative slopes, and then it switches to positive on this side, this is an XY coordinate as well, and it's called a local minimum. This is where it switches from negative slope to positive. And you can see that. Going downhill, then it turns around, goes uphill. New example, 4 minus 3x squared plus x cubed on this interval. So they're chopping our interval. They're saying it only goes from -2 to +3. Find and classify any turning points. Well, first thing I'll do is I'll take the derivative. So this becomes -6x plus 3x squared. Then I'll figure out where the turnaround points are by setting this equal to 0. Now, the things on the right, these both are divisible by 3 and both have an x in them. So you can factor out a 3x, and then left over you have -2 plus x. Set those both equal to 0, and you get x is equal to 0 and +2. Then we will zone test, not zone test, but I guess slope test, is that what I'm calling it? So we'll put 0 here, we'll put +2 here, and then we're going to test these 3 different zones. So we'll pick a number to the left of 0, like -1. Remember that we're putting them into the slope machine, which is this, to see what slopes are happening in those zones. If I put a -1 in these x spots, I get 6 plus 3, so that's positive. So that means we're going uphill in that zone. If I pick a 1 and put it in those spots, which 1 is in between 0 and 2, I get -6 plus 3, which is -3, so it is indeed going downhill like that. And then if I pick 3, I get -18 plus 27, so that is a positive number. So that means that 0 is a turnaround spot, and it switches from positive to negative. So x equals 0 is a local max, and x equals 2 is a local min. Now, the one thing I didn't do is plug the 0 and the 2 back into the OG function to figure out what the coordinates are. When it said find and classify any turning points, let's see what they do in the book. I'm not sure if they want the actual coordinate or not. Oh, they do plug them back in. Okay, so plug these back in to the OG. So put those back into this equation right here to figure out what your y values are. And when you do that, you get 0, 4, and 2, 0. Well, I didn't know they'd be right on the money like that. Okay. So 0, 4 is the local max. And 2, 0 is local min. State the intervals where f of x is increasing and decreasing. Well, we know that information from right here. I already kind of tested to see where it's increasing and decreasing. So it's increasing from negative infinity all the way up to 0, but not including 0. Notice that the bracket doesn't cover the 0. It's turned away from it, so that's not including. And that's going to be unionized with bracket 2 all the way to positive infinity. And then it's going to be decreasing only in that zone right here in between 0 and 2. So that'll be from 0, not including, to 2, not including. State whether the points in part A are local or global extrema. So we already know that these points right here are the local max and the local min. But what we don't know is whether or not they're the global max and the global min. So what you have to do is check the endpoints, -2 and +3. And see if they're any bigger or smaller than the y values we got. And then they were x equals -2 and x equals 3. So when you plug those back in, so if you take into the original function, f of -2, that was 4, take away 3x squared plus x cubed. So 4 minus 3 times -2 squared plus -2 cubed. When you crunch that out, this is -16. But then we have to check the other one as well and say f of 3, if you plug that into the OG equation, remember we're getting coordinates, 3 times 3 squared, gosh, I apologize, 3 cubed. When you simplify that, you get 4. So what this means, since like these numbers here, -16 and 4, look, our local max here was 4 and the local min was 0. So I'm really only caring about the y values. Maxes and mins only are all about like what's the biggest and the smallest y value. This is by far the smallest, so this is a global minimum. Now this one right here, +4, that's the same as this guy right here, which means that that is a local max and a global max. So check the endpoints, see if their y values line up or not. I apologize for rushing, but I have a class coming soon. Use derivatives to show that that has no turning points. So first thing we have to do is split the denominator. We have to do a rewrite. So when you get x over x minus 5 over x, so this is 1 minus 5x to the -1. Then when you take the derivative, y prime, you get positive 5x to the -2, but then bump the x squared back downstairs. So this is the derivative. When you try to set that equal to 0 to find your turning points, you get this. 0 equals 5 over x squared. So then you think to yourself, what kind of numbers could I put in here to get out a 0 right here? 5 divided by what is 0? And you think to yourself, well, you know, maybe a 0. And then you're like, well, no, if I put a 0 right here, then that's undefined. It's not 0. 0 divided by something else is 0, but 5 divided by 0 is not 0. Then maybe like, oh, well, I'll just solve it algebraically. Like I'll multiply both sides by x squared, and then x squared times 0, so I get 0 equals 5. And then I'm like, oh, this isn't working. That's because there are no turnaround points. There's no solution. No horizontal tangents. Horizontal tangents. If you want to figure out where it's increasing and decreasing, like you can take a number line, you know, and we don't have any turnaround points, but I'll put 0 in the middle if we want. And then this is our slope machine, 5 over x squared. If you put negative numbers into x squared, they turn positive, which means that we are going uphill in this direction. And then if you put positive numbers squared, they're also positive numbers. So it's like it's going uphill at all times. X minus 5 over x. So the original equation, x minus 5 over x, The vertical asymptote is when the denominator is equal to 0. So that's x equals to 0. And then the horizontal asymptote is that trick I taught you guys where it's the ratio of the leading coefficients, which is 1 over 1. So that's y is equal to 1. Quick sketch of the function. Vertical asymptote is right here. Horizontal asymptote is right here. And then we know from the derivative it's always increasing, which means cobweb going up, cobweb going up this way as well. All of these tangents are always positive. So this is what the graph looks like.